Hey there, in this video we're going to cover section 6.6, which is normal approximation to the binomial. And we're going to start with this problem that you may have already seen if you took the survey. So the background is that in a study conducted by Psychonomic Bulletin and Review, they presented evidence that people use facial prototypes when they encounter different names. Participants were given two faces and had to choose which one was Bob and which was Tim. The researchers wrote that their participants overwhelmingly agreed on which face belonged to Bob and which face belonged to Tim, but they did not provide the exact results of the study. And by the way, the men in these pictures are not real people. In the first of two studies reported in the paper, different people were given a computer and software to allow them to create faces, and the task was to create a face for someone named Tim and to create a face for someone named Bob. And then these pictures were created based on those other pictures. So someone took all of those pictures and created a composite of what a Tim looked like based on all those pictures and what a Bob looked like based on all those pictures. So that's what these pictures are. So these are not real people. So in the class survey, I asked you to choose the name of the man in the image on the left. And so just to collect my data without any bias, there were different options. Some of you were asked to choose between Tim or Bob, and others were given the option Bob or Tim. So I switched the order in which the name was provided, so in a way to try to eliminate any potential bias. All right, so we're going to go through the 6-step process of doing statistical analysis. Step 1, ask a research question. Step 2, design a study and collect data. Step 3, then explore the data. Step 4, draw inferences beyond the data, and then that's the longest one. Then step 5, formulate conclusions, and step 6, look back and ahead. So let's go back to the beginning. So identify the research question. So in this case is, do STAT 300 students use facial prototypes when they encounter different names? And the reason for this particular question is because notice that here there's no particular data given. There are no results of a study, right? It actually says that they did not provide the exact results of the study. So the data that we're going to analyze is the data from the survey that I created. So what was my survey? My survey was intended for STAT 300 students. So that's why the research question is not, do people use facial prototyping, but it is instead, do STAT 300 students use facial prototypes, because that's the data that I collected was from STAT 300 students. So what are the observational units? Moving on to step 2, design a study and collect data. Once we have a research question, then how are we going to collect the data? So who or what are our observational units? And so we can say the observational units are STAT 300 students, because that's who we are asking information from. What is the variable that is being measured and recorded on each observational unit? So what is the question? What am I keeping track of? So we are keeping track of the name that was assigned to the image on the left. And then what type of variable is this? Is it categorical or is it quantitative? And so think about the responses. So what were the options? You could either assign Tim or Bob, right? Or Bob or Tim, whichever option you get. So, but either way, there are two options. We can say it's categorical. And because there are only two options, we can also say that is binary. So this kind of fits with the binomial distribution, right? Because then you're going to have success and a failure. And so we're going to keep track of that. Describe in words a parameter of interest in this study. Now remember, parameter refers to the population. And so, and a statistic refers to the sample. So let me write that down real quick. So then describing what's the parameter in the study. The parameter in the study then will be the proportion of all STAT 300 students who do what? What is it that I conjecture? Let's go back up to the top. So I said I conjecture that students are more likely to assign the name Tim to the image on the left. And so that would be the parameter then that will be the proportion of all STAT 300 students who assign the name Tim to the image on the left. From here, we can state the null and alternative hypotheses to be tested. So this will be similar to when we did the baby study. So you want to write the null hypotheses, which is the by chance method, and then the alternative hypotheses, which is oftentimes the thing that is the conjecture, the theory that we have. So the alternative hypothesis will be, what would it be? Well, we're looking at two phases and we want to see how do we assign the name Tim. So if things are happening by chance, then that the null hypothesis will be we're choosing the name Tim at random. And so that's going to be our null hypothesis. And then the alternative is we are using visual prototyping and are assigning the name Tim to the image on the left accordingly. So let me write that down. We do have to do it in words and in symbols. So I'm writing the symbols underneath. So H null is then P is equal to 0.5, right? I'm using the P here, or that's what our textbook uses. Sometimes you'll see pi, but let's make sure we don't have the hat. The hat is when you have from a sample. So the null and alternative hypotheses are always written about the population. So null hypothesis is students are choosing the name Tim at random, so you're just guessing. In symbols, H null is P equals 0.5. Why 0.5? Because there are two names. If you're choosing at random, you have Tim or Bob to choose. So choosing Tim at random will be 1 out of 2. The alternative hypothesis is students use facial prototyping and choose the name Tim for the image on the left more often because that's what a Tim will look like to you. So in symbols, H sub A for alternative hypothesis is P, the population proportion, will be greater than 0.5. So now let's look at the data, exploring the data. So in the survey, 22 students, 22 of you answered the survey, and 19 of you assigned the name Tim to the image on the left. So what is our sample proportion or statistic? So calculate the observed statistic relevant for this study and use the appropriate symbol, right? When it's a population, we're using P. When it's a sample, now that's called a statistic, but population is a parameter. From the sample is called a statistic. And so we have P hat, then is our symbol, and it's 19 out of 22, which will be 0.86. So that's pretty high, right? Our hypothesis, null hypothesis, is 0.5. So if we were just guessing and not using facial prototyping, then it should be around 0.5, but we got 0.86. So just based on our statistic, do we have something to move forward with? Yes, right? So we can try to now prove the conjecture, or not prove. We can't prove anything with statistics. What is the likelihood that we are using facial prototyping is leaning more like the alternative hypothesis is happening, right? Students are using facial prototyping and are choosing the name Tim more often. And our sample kind of indicates that 0.86 is higher than 0.5. So we can keep going with our study. So for example, had I said that my alternative, right, is my conjecture is that students choose the name Tim more often, but if my p hat was like 0.4, then I will have nothing to go on. My sample is not indicative of my conjecture, so I will either have to recreate my survey, recollect data, because if this was 0.46, I wouldn't be I will have nothing to do, right? Essentially, it's like my conjecture, oh, my sample is indicating that my conjecture is not correct, so there's nothing to go on. But in this case, right, I have 0.86. It's like, oh, yay, my sample is supporting what I think the conjecture is, so let's keep going. So now we're going to do a simulation, just like we did with the baby study, which is section 5.1. So if you missed that section, which by the way, when I was grading the notes, I did see 5.1 was missing a lot, go back and look at that because that's relevant to this. So we're going to use again the one proportion applet to make the 10,000 simulations for our null hypotheses. And so what does it mean to be a success? A success is selecting the name Tim for the image on the left. If we were just doing it by random chance, by just guessing, the probability is 0.5, 1 out of 2, Tim or Bob. So selecting Tim is 1 out of 2. It's like a coin flip, heads or tails. Failure is not selecting the name Tim for the image on the left, or you could also write it selecting the name Bob for the image on the left. What is the probability of failure? Also 1/2, right? Not selecting Tim means you're selecting Bob, which is 1 out of 2, so 0.5. So Q is 0.5. One repetition is 22 students, right? Because 22 of you were assigned the survey, well, answered the survey. Identify the shape, center, and spread or variability of the null distribution. So you can follow the link that's here in the notes, or I also, in the modules, in the statistical analysis module, I added a few things. So I've added the one proportion applet, which is that same link. I added our z-scores for that are in the back of the book. So the negative z-scores and the positive z-scores, so just so that you have it a little more handy here. So let's go to that link, and it's going to open our one proportion applet. And I don't like how it looks in here, so let's follow the link up here. By the way, if this ever happens and something doesn't load here, it tells you an error, the link is still up here. Although I think my screen is cutting it off a little bit, but the link is always up here. So sometimes you might get an error here that says not loading or something happened. If you click on the link up here, it should be fine. So let's click on that. And there's my one proportion applet. And so we're going to fill it out using our simulation that we just discussed over here, right? For our simulation, success is selecting the name Tim. Chance of success is 0.5. We're gonna, one repetition is 22 students, and we wanna do the simulation 10,000 times. So let's go back to the applet. So in here, probability of heads, I really wish that this said successes, but when you're using this applet, it's heads is success and then tails is a failure. So you'll always see heads here, so 0.5. Number of tosses, that's how many people. So 22 of you took the survey, and number of repetitions. I'm going to do 1 right now just to show you again how this works. We did it for the baby study. Do babies choose the friendly or unfriendly toy, if you remember that? So I'm going to do draw samples, and then notice that it's essentially flipping the penny every time as it tries to do it 22 times. So once it's done, it's going to show us, so it tells me 15 successes out of 22. So this is essentially the equivalent of that survey. So if I gave this survey to another set of 22 students, this could be the result that happened, right? So then it puts a dot there, and I want to do it 10,000 times. So I already have 1, so I'm gonna do, let's do 1,000 first. So I'm gonna do 999, right? Since I already have 1 there, 1 plus 999 will give me 1,000. Now, one thing I want to do is unclick show animation, because then it's not going to be flipping the coin every time. So draw samples, and now it tells me, so this is then my 1,000. Notice here the total repetitions. I've done 1,000. So this is the sampling distribution. So essentially, if I gave this exact same survey to 22 students in 1,000 stat 300 classes, then, which we don't have that many, but in theory, right, this is essentially replicating your results, trying to replicate that sample 1,000 times. And so this is what we do a lot with statistics, is like we have a sample, and then we want to see how likely are these results to be replicated. And so here we are. This is the sampling distribution. So this is as if I gave 1,000 surveys to 22 different sets of students. And so I have my sampling distribution is right here. Now, by the way, notice that this coins, you can say hide coins because this just gives you the latest coin flip. So the 1,000th. So the very last one, that's what this is. So I don't need to see it. So we can just hide the coins because all I want is really the graph. We also, this is showing us the number of heads. So when I want to see where is it centered at, it appears to be centered around 11, right? And does that make sense? Yeah, we have 22 students and we think the probability is 1/2. So it makes sense that it will be centered around 11, right? 11 is half of 22. But let's do 10,000. So I already have 1,000 there. So let's do 9,000 here. It's really important to not have the show animation. Otherwise this is going to take forever because it's going to be flipping the coin 22, right? 22 coins 9,000 times. So if you forget to unclick that, you're gonna sit here for a little bit. So draw samples, and there they are. So now I have 10,000 repetitions, and this is what my sampling distribution looks like, right? So this is essentially as if I had 10,000 sets of 22 students answering the same survey that you answer. This is giving me the number. We are after the proportion, so change that to proportion, and now notice that it changed it to proportion, so 0.5, which makes sense with what we thought the probability of success is. So back to our note is asking identify the shape, center, and spread. So it looks bell-shaped. The center is around 0.5, the proportion of success, and we can see that again by looking at this. But you can also click on summary stats here, just like in StatCrunch. When we want to find the mean and standard deviation, we select summary stats. The mean is exactly 0.5 in my case. Now if you're doing this on your own, which you should be doing also on your own, you might get 0.498 or 0.501. That's okay as long as it's around 0.5, because that makes sense. That's what we're assuming, right? We're assuming the null distribution is 0.5 and a standard deviation of 0.106. So yours may be 0.118, 0.104, so something like that, but it should be around the same number, 0.106. So let me actually take a screenshot of this and we'll put it in our notes. Right, back to our notes, I can just paste it in here, and now let me fill in so we see it's bell shape, so normal distribution, center around 0.5, and with standard deviation of, and now I can fill that in. So the standard deviation is 0.106 of my sampling distribution. So let me write that in for the sampling distribution. So this is the simulation. And so there we are. Explain why the value of the center makes sense for the simulation. The center of 0.5 makes sense because if students are choosing at random, half will randomly choose the name Tim, right? Bob or Tim, so 1 out of 2. Now looking at this distribution, where is our sample statistic? Remember, our sample statistic was 0.86. So where is that in our distribution? It's going to be way over here, right? So if we go back to the simulation, so you can go here as extreme as, if I put 0.86, it's going to tell me where it is. So way over here. So the probability of that happening is very small. So if I'm doing things at random, it's very unlikely that I will get 0.86 as a statistic, right? So notice that it says only 5 out of 10,000 times it shows up. So that means it's very unlikely. If things were happening truly at random, if you guys were just guessing on the name, it's very unlikely that 22 people, right, that 19 of them choose the name Tim if things are happening at random. That's what this means. It's way out here. So, but let's do it with the empirical rule or our z-scores. So where does our z-score fall?
And so that's what this next part is, the strength of evidence. So calculate the approximate standardized statistic. So the standardized statistic, the general formula is our observed statistic minus the hypothesized parameter divided by the standard deviation of our sampling distribution or null distribution. So here, p hat minus p divided by the standard deviation. So our sample statistic was the 0.86, 19 out of 22, minus our hypothesized parameter. Our hypothesized parameter comes from our null distribution. We said p is 0.5, so that's what we're going to use, the population parameter, divided by the standard deviation. The standard deviation, I just found that out. What was it? It was 0.106. So let's put that in here, 0.106. And what does that equal to? Let's put that in our calculator and find out. I got 3.39 if I did that correctly, which is really big, right? Remember, from the empirical rule, observations that fall more than 2 or 3 standard deviations from the hypothesized value are considered to be in the tail of the distribution, or also very unlikely. So that's definitely more than 3. So if your standardized statistic larger than 2 or 3? Yes. Our z-score is, so the probability that x is larger than 19, I guess I should say that p hat is greater than, I'm using numbers there, but I should really be using the proportion, 0.86. Let me get the hat in here. So the probability that p hat is greater than 0.86 is the same thing, it's equivalent to saying the probability that z is greater than, this is our standardized statistic, the 3.39, which is, from the last section we learned, when for greater than, we have to do 1 minus the probability that z is less than 3.39. And so let's look at our z-score page, which for that we can go to our module, and I just loaded them on your statistical analysis tools module. So 3.39 is positive, so let's click on that one, the z-score positive, and then we're looking for 3.39. So let's scroll until you get 3.3. So there's 3.3 and then 9, so the last one, right? So let's see, 3.39, so 0.9997. So that's the one that we're after. So that's our probability that our z, or standardized statistic, is less than 0.9997, or less than 0.339. The probability is 0.997. So let's go back to our notes and type that in here. So 1 minus point, what was it, 39 and 7, and then notice that that's going to be very small. So I got 0.0003. So very small probability, right? Very unlikely. So according to this criteria, is the observed value of the sample proportion surprising when a null hypothesis is true? Yes, right, it should be surprising. Now remember, the null hypothesis is that things are happening by random chance. So we're just guessing. So is this surprising then if we're just guessing? Yes, because if you're just guessing, you should expect about 11 or 0.5, half of the students to choose the name Tim, but this says that that's not what's happening. So write a paragraph as if to a member of your family who is not taking statistics, summarizing the conclusion that you will draw from this study in your simulation analysis. So if someone has not taken statistics, right, you wouldn't mention the word, maybe average is fine, but you wouldn't say what are some things like standard deviation or empirical rules. So try to get rid of any statistics lingo, any statistics jargon that you could use. So try to put it in plain terms, like what can you conclude from this study. Now look back in ahead. Let's step back a bit and think about the scope of our inference. Are there any improvements you would suggest for how the data were collected? Are there any other changes that you would suggest for this study? Could you suggest a future research study that you will be interested in investigating based on these results? Do we use facial prototyping, do you think? This study suggests that we do, right? This was very high, 0.86. So 19 out of 22 students selected the name Tim for the image on the left. So there was something that led you to assign the name Tim to that image. And so think about where else do you use those kinds of things. And I know it happens to me in my personal life. I am Latin, but when people hear the last name Owens, or when they see me in the class schedule as Owens, right? Like, were you expecting me to be your teacher, someone who looks like me? So likely not with the last name Owens, right? You probably are like, oh, not a bad thing. It's just that we have some preconceived notions based on names of what people will look like. And so I want you to think about stuff like that. Like, where else does that happen? Some things that people have said in the past when I've taught this class is like, what about for women? Or what about, for different like ethnicities and things like that? Like, how will this change? So those are things, right? From one study, from the results of one study, another study spins off, like, because you get more questions like, why is that happening? Does this happen in other instances? How does that happen in other instances? And then you can see how other statistical studies can be developed. Now here's the above study of binomial probability distribution. Recall that a binomial probability distribution has a fixed number of trials, so yes, it qualifies for that. Trials that are independent, yes, right? You choosing the name Tim did not affect one of your classmates choosing the name Tim or Bob, so they're independent. Your choice of name does not affect somebody else's choice of name. Trials are each classified into two categories, commonly referred to as a success and a failure. Yes, right? You had two, Tim or Bob, and choosing Tim was what we classified as a success. Trials with the property that the probability of success remains constant. Yes, each one of you, the probability didn't change. So you choosing the name was half, somebody else choosing the name was also 1/2. So the probability didn't change. Now, does it meet the requirements? The requirements to approximate binomial probability distribution are that the sample is a simple random sample of size n from a population in which the proportion of successes is p, or the sample is a result of conducting n independent trials of a binomial experiment with probability of success p. So here, would it be a simple random sample? Well, we're going to say yes. Technically, you guys are a convenience sample because you're my class, but it is a simple random sample of ARC students. And so the key condition to be able to use a binomial probability distribution is that the number of successes has to be more than 5, and the number of failures has also have to be greater than 5. I'm sorry. So we had 19 successes, n times p was greater than 5, and n times q was greater than 5. So in this case, our n times q is not greater than 5 because we had 3 failures. But because that's where the simulation kind of came into, the simulation helped us be able to use the central limit theorem. So when these conditions are satisfied, then we can say that the population parameter, the mean, or in this case p, the mean is n times p. So the successes and the standard deviation is the square root of npq. Check if Bob and Tim's study can be approximated with a normal distribution. In our case, right, we said NQ was not greater than 5, so just by the standard rules, we wouldn't be able to, but then that's where we bring in a simulation to see, does it develop a normal distribution? And in our case, it did, so then we can use it. And then try this example on your own and see what you come up with. Sleepwalking. So this is, assume that 29.2% of people have sleepwalked. So this is your population parameter, right? And then go through and read it and find the probability that 455 or more of the 1480 adults have sleepwalked. So is this result the result of 455 or more significantly high? What does the result suggest about the rate of 29.2%? So if you were going to use the one proportion applet, then you would assume this will be your null distribution, the 29.2. So if I was going to use a simulation approach, instead of 0.5 here, I will use 0.292, right? Because that's what is telling me that is the assumption. All right, so try this one on your own using the probability, the binomial probability, and see what you come up with. I will record a video with the answer, but try to do it on your own and then go to that video. All right, email me if you have any questions.